Dear colleagues, today's day of our seminar. Now we have a air alarm, but our seminar still working. And today our lecture is Dr. Patrick Navard, who is graduated in material physics from National Institute of Applied Science in Lyon in 1978 and in applied biology from Lyon University the same year. He obtained his PhD from École des Mines de Paris in 1982 and doctorate of science from Lyon University in 1983. After his doctoral studies, he conducted postdoctoral research at the IBM Research Center from 1983 to 1984. He joined the National Center for Scientific Research, CNRS, in 1984, where he served as research director many years, from 1989 to 2019. And since 2019, he has been an emeritus research director of CNRS. Dr. Navard is an expert in physics, rheology, and processing of polymers, including biopolymers. He established and led for 15 years the European Polysaccharide Network for Excellence. His current research focuses on the impacts of plastic additives on health and environment. Dr. Navard has received multiple awards, including the annual prize of both the French Rheological Society and the French Polymer Society. Dr. Navard served on the editorial boards of Cellulose Chemistry and Technology and Carbohydrate Polymers. He has supervised more than 30 PhD theses and over 45 research projects. Additionally, he is actively involved in the scientific communications and the forming of the Science per 206 associations, which has organized more than 310 public events. And dear Dr. Navard, please, microphone is yours.
Okay, thank you very much. Thanks for this very kind introduction. I'm honored to be invited to give this lecture. So I will share my slides. Is it fine like this?
Yes.
It's okay. Perfect. Yes. So I will focus on plastics additives, the uses and impacts on health and environment. This is a topic I started about 5 years ago when I decided to change totally my field of research. Previously, I was, as you said, deeply involved into polysaccharides and natural polymers, where for quite a long time I was the head of a large network in Europe. There was nobody from your country for the moment. Why is it not working? Okay. So, in fact, this lecture will present results which are been obtained in several different recent projects. There was 2 French research agency projects, one around the understanding and preventing toxic non-intentionally added substances, or NIAS. I will speak about this later. Formation in commonly used plastic parts. I'm coordinating this project. There was a second project, still from the French Research Agency, on environmental dynamics and impact of contaminant cocktails originating from plastic in soil ecosystems. I will not speak about that, about all the results which are coming from this project. I will say something about the last 2. The third is about the potential migration of plastic additives through human skin. So I will describe the results. We do have that. We will also, sorry, I'm a bit fast. I will also describe results from the French project, for the first project about NIAS, and also for the last one about the identification and quantification of the presence of phthalate in a university hospital. So as you know, we all know that plastics are absolutely everywhere. So we are among a sea of plastics. You are aware that right now there is a large meeting, a governmental meeting for trying to help solving some of the problems associated with plastics. They are everywhere, and they are helping our life a lot. They are also having some dangers, as you know. So they are everywhere. You find them in cars, in housing, in tires are plastics. That's the definition of plastic in many medical areas, for sport, for everywhere, computers, whatever. So what I will tell you during the moment we will be together will be divided in two parts. The first will be an introduction to plastics and additives and contaminants. So the first, I will simply define what is plastic material. I'm sure all of you knows, but okay, that's good to recall. And then I will briefly say something about additives and contaminants. That will be my introduction. Then I will focus on three different topics, which are, of course, linked to additives and contaminants. There are three different research projects. The first one, which is number 3 in my slide, that's the in vitro evaluation of polyethylene additives in human skin. The second will be the understanding additive degradation pathways and formation of NIAS in polystyrene. And the fifth one will be the identification of phthalates presence in medical devices in French hospitals, and in particular in one which is close to where I'm living, near Nice, in the southern part of France. So let's simply speak about plastics. I think that's useful to recall. Plastics, I took two definitions. They're all the same. Plastics are usually defined as a polymeric material to which additives may have been added. In fact, a plastic, this is a polymer plus additives. Now, most of the time, you do have additives. That's very rare that you're using a polymer without any additives at all. For the French government, that's the same. That's plastics mean that mean a polymer to which additive have been or other substances may have been added, capable of serving as the main structural component of a final materials and object. So plastic, I recall, there's a polymer and additives. Today, I will not speak about polymers, not much. I will just cite the polymers we will use. But then we say something about the additives. So let's look at additives and contaminants, which are present in a plastic material. So what we have to realize is that up to sometimes 30% of the plastic mass, that's additive. Especially, for example, if you wear glasses, the frame of your glasses is in plastic, most of the cases they are in cellulose acetate, you may have up to 30% of additives in. So that's not negligible at all. That's a very important part of the plastic, the additives. We can, let's say, separate what is in this plastic outside the polymer in 3 categories. So the first one is the blue one. So the blue one on the right, the additives, so they are added with the intention to reach certain properties which are absolutely needed for making an object. So these additives, they are added by the persons or by the companies which are making the product. So there are many additives. As you will see, there are thousands of additives. So they are with very different properties. The additive depends on the polymer and, of course, on what you wish to reach. So you have on the left antioxidants, for example. They are important. Most of the polymers do have antioxidants. Antistatic, as soon as charges are around, you may need to remove them, especially in the computer science or everything linked to where electricity is around. You have slip additives. For example, slip additives, they are very important if you want to wish to make films, if you want to do blow molding, where you are blowing a film through an annular extrusion die, then the film should slip on the surface of the die of the die, and then you have to add a lot of slip additives. Plasticizers, if you want this to be a bit more soft. Biocides, if this has to be used, for example, in a hospital environment. For sure, pigments, most of the material, not all, but most, they have colors. Where there is a clear exception, which are the PET, polyethylene terephthalate bottles, where there is no pigment. But most of the time, you do have a pigment. If you look around you, you will have a lot of things in plastics, and they are all colors, which is the beauty of plastic material to make colors. Filling agents, temperature stabilization, dyeing additives. There are many, many additives. In addition to these additives, you may have close to your polymer, without adding anything, traces of initial substances. This is what is in black. Monomers, catalysts, solvents. You may have traces of that. So you do have always traces of that in more or less quantities. So you have the additives in blue, you have the initial substances, monomers, catalysts, solvents, which is already present in the polymer when you collect it from the manufacturer. But then you have other substances that was not present initially, and you didn't put them. They are called non-intentionally added substances, NIAS for the acronym. These NIAS are created by many different ways. They can be created products due to the reaction between additives, for example, if you have traces of catalyst. There can be some impurities that will arrive simply by the additives itself. The additives are not pure. And then also a lot of degradation products. These NIAS, these added substances that you don't want to see in your material, in your product, they are creating a lot of difficulties because sometimes they can be in rather large quantities. I mean a few percent sometimes. And you don't know, you have no control of that. You have the control of the additives. You may purify more or less well the polymer to avoid the initial substances, the monomers, the catalyst, and the solvent traces. The additives you control, but the NIAS you don't control them at all. And this is especially important when you are recycling. I will not speak about recycling, or not a lot, but when you are mechanically recycling polymers, then you are creating a lot of NIAS, hundreds sometimes of NIAS that you don't want to be there. Just an example with cellulose acetate, I put the frames of glasses. Some of the additives which are there, they are for uses which are clear, for uses in films. So you may change you want to have flexible, soft, hard, elastic, hydrophobic. For all these reasons, you have to add additives. Some of them, we don't know exactly if they are toxic or not, but for some of them, we know they are toxic, and they are there. For example, glass frames, they bear many, many colorants. Just an example, how you can create NIAS. So that was a very simple experiment I did at the beginning of about 4 years ago when I started to move into this area. What I did was to take an initial polypropylene. That's in blue. That's the second from the bottom. So I took the NMR trace of my initial polypropylene, and then I added four different, very, very common additives. Some antioxidants, some UV, anti-UV, some brightness, very classical one, other concentrations which are classically used in industry. So what you should have when you are mixing this at 220 degrees in exactly the way you are doing in industry, you should have a trace of the mixture, which should be the trace, which should be the sum of the traces of the four additives plus the initial polypropylene. And this is not what you find. We found new substances. You see new peaks coming due to the reaction between these additives during the processing. So these are the NIAS, how they are produced. The plastics, that's a cocktail of contaminants. 4,000 additives are known. 900 are in the positive list in European Union for food contact. What is called the positive list is an additive you can use for food contact. And there are 10,000 chemical products which are used at one step or another. The problem is that the toxicity of most of these chemicals is not known. And also, another interesting thing is that the final company manufacturing a product does not necessarily know which additives were added to the polymer, simply because there are different steps with different companies, and each company is keeping the additive they are using, let's say the recipe. This is their recipe, and they will not share with any other company. I will finish by just illustrating what these additives are in terms of safety. There is a French regulation agency for safety, which is making recommendation on many things. But one of the things they did in November 2022 is this ban plastic materials from household compost. And when they say plastic materials, they say even biodegradable, compostable materials should not be put in compost. And the reason, is that is in red. Polymers, residual monomers, additives, or inorganic fillers are there, and they will stay there even if the polymer will degrade. So these additives are posing some difficulty. If we look at the production of plastics, you all know that it increased a lot. In 2020, 24, that's about 450 million tons of plastic, but it is planned that 600 million tons of plastics will be produced in 2040. That's why many countries are advocating the fact that we should try to decrease that. Some countries, the ones which are producing oil, are saying no, we will continue to produce plastics. It is estimated that 20–30% are ending in nature, oceans, soils, and rivers, and less than 10% are recycled. I made a small calculation, and if with this consider that all plastics are, all plastics have 2, 3, 4% of additives. If 20% are ending in nature, then you know how much plastics is produced per year. So you know how much additives are ending in nature per year. And you calculate that about 4 times more additives mass is lost in nature than pesticides sprayed in cultivation fields. So we should pay attention more as scientists to the fate of additives, to my opinion. So the first topic will be looking at these additives in terms of human skin. This is a project which is part of an Ukrainian PhD student, Veronica, who is online, with different other laboratories and, of course, researchers. So polymers, additives, and human health. That started from a very simple question I asked Veronica, which is when you are holding a plastic piece, whatever it is, how can we be sure that the additives which are inside are not migrating into skin? That was just a simple question. Can organic additives migrate from plastic parts into human skin? And we know that we have the additives, the intentionally added substances, but also we have the one we don't like, the monomers, side reaction products, degradation products, impurities, contaminants. All that is in the part. What we will really go into the skin. So we started by looking only to additives. For NIAS, it's more complicated. So we looked at additives. So what we did was to put a polyethylene plus additive disc on a piece of human skin. The human skin is a very complex film, somehow we can call it a film, with different parts which have very different properties and activities. At the upper surface of our skin is the stratum corneum. It's a very thin part, but very, very important. It's a very complex structure, like a wall, which have the object of repulsing anything which is coming from a foreign body. Okay, so if you are exogenetic, you will be expelled from the skin if the skin is intact. Right under, you have the epidermis, which is a bit thin, or not too large, and then there is a large dermis. For skin, when we speak about large and it's a bit not so large, but okay, the dermis is the largest part of the skin, and inside you have many things: the sweat glands, they have follicles, the blood vessels which are running there. There are many things. So the way any material will go inside the stratum corneum is either it will be intercellular, you have small cells there, and it has to go around them, or you go through them, or you take the advantage of having a follicular, which has a hair which is there. So that's the way our additives might go through epidermis and dermis, which is what we would like to see. How did we do this? So what we did was to start compounding and produce polyethylene blends. So we started with PE, low density PE. We ground it. To grind PE is rather complicated. That's very low TG. It's very soft. It's very complicated. So, okay, Veronica found all the right procedures to do that. It has, of course, to be processed in liquid nitrogen. And then we add 1% of 5 additives. They are very common additives. Okay, some are antioxidants. 3 are primary antioxidants. 1 is a secondary antioxidant, which is working with one of the 3 others, and 1 UV protector. We put them at a concentration of 1%, which is more or less the concentration you can find in industry. And then we mixed the whole thing. We found, or we selected these additives simply because they had normally a very low toxicity, at least comparing to others. As you can see, Garphos has a low acute toxicity, but there is some concern about degradation products as usual. The 2 other antioxidants have also low acute toxicity. Chimasorb has a low moderate toxicity. Again, always some concern about some problems. UV 326 is restricted a bit in the EU because it has also some potential endocrine disrupting effects. But they are absolutely used in many, many places and many products. So we mix the polyethylene, our additives, and then we will, this mixture will be heated in an internal mixer. We selected the temperature, 210 degrees, classical velocity of 20 rounds per minute, and for a short time of 5 minutes. When we did that, we got a sort of our mixture, which was a bit elastic. It's polyethylene that we had to cut, and then we put that mixture into a press to produce on the left discs of about 1 millimeter thickness and 1.3 centimeter diameter, which will be used later to put on the skin. So we have to prepare the skin also. So the skin was prepared in different ways. So either we took the full thickness skin as it arrived from donors, or there was another uh, process which was to cut part of the dermis, and a third way also to damage the skin. All that was put in a France diffusion cell. So that's a very simple system somehow, system which is kept at 37 degrees to mimic real skin. There is stirrer, there is a liquid, which is a buffer, saline buffer, phosphate saline buffer, plus some twin 80, which was added for helping collecting potentially the additives. And then there is a sealed chamber where there is the skin. Above it, there is the polyethylene. And then the question was, shall additives will move from the skin, from the polyethylene to the skin? The experiments can only last for 24 hours. Above that, the skin is damaged. So what are the first results we did? We had intact skin and damaged skin. And then we looked at how much we can collect, how much additives we can collect in the epidermis. So you see that, so we use these 5 different additives. The colors means series 1, series 2, series 3. So the green, the blue, and the yellow. There are 3 different experiments. What you see is that some additives, they are moving much more into the skin than others. Clearly, UV 3 to 6 is heavily moving into the skin, while, for example, on the right side of the graph, Erganox is not really okay. We don't have a lot of additives migrating into the skin. What we can see is that from damaged or intact, there is not such a large difference. There is a small difference, but not such a large difference. So it was not clearly something very critical. We also, when we said intact skin, that's the one which have been with a very limited amount of dermis. We also got results with a full skin, and we found that we will then use that for the next experiments. There was no need to damage or to cut the skin. That was our preliminary results, showing that indeed, unfortunately, the additives, they are moving into the skin. We can calculate easily how much of the additives migrate in 24 hours into the skin. And we found that in the worst case, a bit less than 1% can migrate in 24 hours in the skin, which is quite a lot, 1% in only 24 hours. So we decided then to use a full skin with the idea to separate then after the additives have penetrated the epidermis and the dermis. So that's a bit okay, that's surgery somehow, but it's possible to do this. Same experiment. We put the polyethylene plus additives on the thick skin, the full skin, and then we will then after cut epidermis and dermis. These are the results. So we had 3 donors where we did several experiments for each of the donors, and we see that for the 3 donors, we have more or less the same scheme, which means that the some chimasaur, for example, is moving, is very present. Some are not penetrating much. So how can we explain that? So first, we were happy to see that whatever is the skin donor, the results are very coherent. We don't have a lot of dispersion. So the migration depends on the molar mass of additives. That's a bit clear, you know. For the additive to penetrate into the skin, it has to be small to move through the polyethylene and to move through the skin. So clearly, when you plot the migration rate on the left to the molar mass of the additives, the lowest mass somehow are moving more into the skin than the large masses. There was another also clear phenomena, which is the lipophilicity. Of course, the lipophilicity is playing a role when you have a low C log P value, which is some low lipophilicity, sorry, they tend to migrate more into the skin. Okay. So these two effects are having an effect. So clearly on the conclusions we showed that organic additives from PE can penetrate the skin epidermis over 24 hours with a maximum migration amount of 1.6% in 24 hours. Two of the additives, Chimasorb and Dirganos 1010, also penetrate into the dermis in small concentrations. And the permeability of additives to the skin is influenced by the balance between their molar mass and lipophilicity. The more lipophilic and larger molecules, they tend to accumulate in the upper layer of the skin, and that's reduced their migration, while smaller and less lipophilic molecules, they can penetrate the skin very easily. There maybe other factors can also be at stake, such as the shape. So this is a work we started, and of course there are many questions around for example, what is the kinetics? We should also use more additives to see whether these first results are really something which is really how it works. And we also have to look at other factors which may affect the penetration of additives into the skin. The second topic is around polystyrene. We were interested by looking at non-intentionally added substances, this NIAS in polystyrene. So this is a work that was performed by postdoc of us, Sasha. So polystyrene production, that's about 20 million tons per year, and that's very poorly recycled, if not recycled at all. So the polystyrene has a lot of added substances, additives that you are putting, like colorant and a lot of functional additives, antistatic, curing agents, flame retardants, plasticizers, lubricants, stabilizers, blowing agents, and so on. But simply because polystyrene is used in many, many different applications, insulation, for household, for bottles, and so on. So we know that if some NIAS are present, it may affect different properties of the material. It may affect the penetration of the barrier to water, mechanical properties. It may affect the flame retardancy properties, how the UV are acting, temperatures, and so on. And we know also that the NIAS presence, that's something which is, of course, may have some, let's say, effects which are not good on health, on environment, and that is preventing recycling. So the loop which is below is simply showing NIAS and closed loop recycling. We use the example of PET because polystyrene cannot be recycled like this. So we start from pellets. We do preform. You do the bottles. At the bottle into you have water. The finished goods. It is it can be recycled. You have rPET flakes, which means recycled PET flakes, and then you do it again. The problem of that loop is that at each loop, you are adding more and more NIAS. So now let's come back to our polystyrene. We are interested in our polystyrene. We will have to extract the NIAS, separate them, purify them, identify them, and know how much are present. So for this, we used the virgin polystyrene, 3 very classical additives, 2 antioxidant, primary, secondary, and a UV stabilizer. Again, all that is mixed with the same machine that was shown before, this internal mixer. So the mixing conditions are the one classical for polystyrene, okay, 210 degrees, 10 minutes, 20 RPM. And then Sasha found a very efficient way to extract these additives, extract this NIAS with a solubilization and precipitation without any heating. So the strategy is there. That's under publication with chloroform. That's second step with methanol hexane, sonication, filtration. Then with reduced pressure, 40 degrees, and then you collect additives and NIAS. We use polystyrene, which was great for molding and extrusion, but I think that any other polystyrene would do. So what did we found? How we can compare this new method to the others? On the left side, you have different properties, grinding, number of cycles to extract, and extraction time, temperature, filtration time, and so on. And yield, okay, of course, which is very important. The dissolution and precipitation, the next 2 columns, are coming from papers where you see that somehow it's a long process with a low yield. The best way is the supercritical fluid extraction, where you have up to 100% yield, but that's supercritical extraction. That's a bit complicated to perform. With our new method, which is simple dissolution and precipitation, we have at room temperature, 1 cycle, very quick, less than 3 hours, not much solvent is used, and then we're able to extract 96.6% of the additives we put in. Okay, so now let's look at the intrinsic NIAS in polystyrene. So we found that mostly we do have dimers of styrene. Normally we should have that, but it was easy to say that 75% of the impurities were dimers of styrene, a bit of trimers, and a smaller amount of quadimers. And the impurities in polystyrene, that's about we found 7.3 milligrams per gram with 7 replicates. In the literature, that's about what is found. Okay, so we were let's say what is found was found by other people, and there was no impact of recycling. To recycle, we simply reprocess several times, and we found that okay, this was not changing. We are not producing dimers of styrene during the recycling. Now, we looked at the additive stability. Again, we extracted everything which can be extracted from this material, and we found that there was no NIAS for 2 of the additives, the UV stabilizer and one of the primary antioxidant. Very stable. But for the third one, the agaphos 168, the secondary antioxidant, it was degrading during our processing with 2 major chemicals, phosphate, butyl phenylphosphate, where the toxicity is unclear. I mean by unclear that some reports are saying it is toxic, some are saying it is not toxic. And the second one was butyl phenol, which there is very toxic. So we had this degradation of agaphos 168 during our process. We were creating NIAS, and one of them was dangerous, for sure. I will move on this. So the conclusion is that, okay, we found, Sasha mainly found, a new extraction method, simple and fast, which can allow very quickly to assess polystyrene quality, recycled or not, if it can be recycled, including for food contact. That's precise identification and quantification with NMR, GCMS, and LCMS. And the degradation pathway, extraction, degradation percentage, temperature dependency, and synergetic effects were identified. I didn't speak about synergetic effects, but clearly there was an effect. the secondary additive was less degrading in the presence of the first one. So we were able to add to investigate multi-additivated materials, including flame retardants. But I didn't present. I have no time to present the results for flame retardants. The last part is to look at the presence or not of phthalate in medical devices in French hospital. And this was a project by Christian and Sacha. So the context is simple. Phthalate, that's a very classical additive for plastification. That's emitting friction also. And it's used in many different medical devices, but especially in PVC. It's very bad, phthalates. They're carcinogenic, reprotoxic, and mainly endocrine perturbators or disruptors. We looked at one of the phthalate, the diethyl ethyl phthalate, the DEHP. That's the most common one. And we look at are they present in the medical devices which are in the Nice hospital, and how can we compare with previous studies from past decades in France? We focused on neonatology. So neonatology, it means that children which are born much in advance and they cannot live without any help. They have to be helped for nutrition. They have to be helped with breathing. And so they have to be put in a special conditions until they reach the age to be able to live alone. So we extracted 7 different parts: enteral nutrition tube, syringes, pumping sets, catheters, and then some packaging, green and white, and then also the milk collectors for breast pumps. The mothers, they have to extract their milk to give to these very young children. We first identified the different materials. We collected parts, but we had to identify them. So you see that there are different polymers: polyurethane, ethylene vinyl acetate, silicone, PVC, polypropylene. Okay, you see that's different type of polymers. There are not so many. We found 5 different polymers, but okay, they are present a bit everywhere. We extracted again with the same procedures. Insoluble polymers, we have different polymers, so we have strategy for each polymer. Insoluble polymers, they have some extraction solvents. Soluble polymers, solubilization and precipitation. So that's the classical way to see what is inside a material. And that's what we found. We found that all the samples, we looked very carefully. Only one, that's the right column, had traces, but it was below the quantification limit. So we can say nearly no. There was no phthalate presence. We found that the yield also, that's what is red, is higher when dyes are present. That's probably due because we're extracting the dyes also. So that's very good results. And especially if we compare to previous years, 2004, all the materials that were in the hospital, in this type of hospitals with neonatology, that they had 16 to 37% of phthalate. And we know that about 80% of these phthalates, they are going to the children. In 2014, there was a slight improvement. There was a bit of material without phthalate, and they were only low, with a very low contamination. And then in 2024, only traces, which means that the use and presence of phthalate have decreased a lot over the last decades, which is a very good point. It means that all the efforts which are done from the manufacturers and the regulators to push the limitation of endocrine perturbators are working. This is very encouraging, in fact, these results. The first 2 were not very encouraging, but this one is. So my message is that polymer communities, they are not paying enough attention to additives. That's a very important part of the manufacturing of plastics and the safety of plastics. Of course, this is a complex matter, considering the very large number of additives and other chemicals used for preparing plastics. It's complex is the identification and quantification of NIAS, sometimes in large numbers, in small with a very low amount, in particular when plastics are mechanically recycled. Even more complex are the degradation path of these additives, which depends, of course, on the way degradation occurs. If it is UV, it is in marine environment, it will be very different paths or in your body, and that's a complication. But even more complex is the toxicological evaluation of cross effects when different additives are present. I would like to thank again all the scientists who participated to these studies. I don't want to forget the many ones I didn't cite because they are still engaged into soil and marine experiments, and they didn't speak about this. Okay, we are putting in different compartments of the soil plastics. We prepared ourselves, which are well controlled in terms of polymer and additives, and again in marine environment, with corals sitting on our polymers, and we will very shortly look if additives are moving in. And I'm thanking you for listening to me. Thank you.
Thank you very much for your very interesting lecture. So, dear colleagues, we have time for questions. Do you have? I don't see.
Maybe the question was very clear.
Yeah, but okay. You talked about transportation of additives through the skin.
Yes.
But what about transportation of additives through the solvents in the bottle, for instance? If you use a bottle for Pepsi Cola or Coca-Cola, of course, this solvent can extract additives from plastic. Do you know something about this type of transportation of additives to the body of human?
This is well studied and this is well regulated. Of course, we are now in food contact or even in the cosmetic when it is not food contact. This is something that is absolutely regulated. You have limits for each of the additive, limits of migration into the food, and that depends on the type of the food. Okay, if it is meat or if it is oil, or that will be different. So this is well regulated, and for sure, additives are migrating into food or into liquids, but this is controlled. What is not controlled is through the skin. When you are putting let's say, a cosmetic over the skin, there is a small control of that, because if the cosmetic is penetrating in the skin, then it is a medicine, and that's another story you have to have. So this is controlled, but for not for a cosmetic, but for simple plastic material. For example, the computer mouse that I have with close to me that I'm using every day, there is no control of that. The same as clothes, technical fibers for clothes. There is a control about irritation of the skin, but nothing about the penetration inside the skin. That's what we wanted to show. And there is another paper. There are two other papers, in fact, where they looked at the same as us for same reasons. There is no regulation. Nothing is known. And these two papers are finding the same as we are finding, which is that in very short time, there is a migration of additives into the skin. And now the question is where it is going. We showed that nearly all are going into the epidermis. Some are going in small quantities in the dermis. Now, is it blocked there, or is it going below where it can go to the blood circulation. That we can't see that because 24 hours is too low. But in other instances, when you look at the blood composition, you found plastic additives in. It can come from different reasons, which is, for example, drinking and eating, but it can also come from the penetration through the skin.
Okay. The most usable device in our life, I think it's a mobile phone. Mobile phone and cover to the mobile phone, and you use it all the time in your hand. What
Yeah,
about
sure.
additives? What about additives and transportation and regulation of mobile phones and covers for mobile phones?
I don't know any regulation for this in terms of migration of additives.
But it's
I
possible.
don't know. I have no idea. What is regulated if you're using it in very large quantities in Europe is you have to declare under the REACH, uh, under REACH, you have to declare how much you're using and what is the toxicity. Now, I don't know if there is a regulation for skin penetration. I've never heard about this.
Mhm.
I don't know. I don't think so. There are other regulations for a phone with something about electrostaticity, about the amount of heat you are generating and things like this. But I'm not sure that you have. I've never heard about this, yeah.
Okay.
Which is annoying, maybe.
And what do you think about the most promising type of plastic for the future, polymer and additive, biodegradable type or other types? If biodegradable, which kind of plastic of degradable type? What do you think about this?
The most used biodegradable plastic at the moment is PLA, polylactic acid. It is bio-based, nearly fully bio-based, and it can be degraded in industrial conditions. It means that if you're leaving it in nature, it will never degrade. But it is biodegradable material. Now, if you look at the amount of additives you have in, that's one, it has a lot of bad additives inside. So, you have a lot of publicity for PLA showing, wow, it is Coca-Cola did it. I think they stopped that, but okay, they did it for many years. They were showing that these bottles are very good for nature because they are biodegradable and they are also coming from natural resources. But they were not saying that it's full of additives. That's what I said here. Polymer communities are not paying enough attention to additives, I think.
I think,
It's not because it is biodegradable that it's not without dangers for additives. That's also the message from the French Safety Agency. Do not put any biodegradable or compostable polymer in your compost because of the additives.
yeah. Yes, I understand it. Yes, it's very important. I think I'll use this information in my lecture for students of Kharkiv University, because I have a lecture concerning green chemistry and also for concerning plastics. Thank you very much.
Okay, thank you. Thank you very much. Okay.
So, dear colleagues, if you don't have other questions, no. Thanks again for your very interesting lecture, and have a
Thank
nice
you.
evening.
Thank you very much. Bye-bye.
Bye.